Excellent. Okay. All right, guys. So welcome to week 6 or 7. I've lost count at this point. Today's going to be a very important day. We're going to be learning a very important tool for not just this class, but when we do quantum field theory. And in fact, usually when people, if you're an undergrad or a graduate student and you're about to register for quantum field theory, usually what you do is you look up, what should I know before I take quantum field theory? And what I'm going to show you today pops up on every list because it's a very important tool. So we're going to learn about creation and annihilation operators, or raising and lowering operators today. Now, we saw them in the context of angular momentum, but I feel like that was very abstract and you guys really didn't get a sense of how they work. So today, I hope it becomes very clear how they work, and we're going to do explicit calculations with them to derive energy levels for the harmonic oscillator, which is a very important system. And I'll give you a more conceptual overlay in a second. But before, let me just give some logistics. The first logistic is no problem set this week, again, and no problem solving session today. Instead, I've put aside an hour to talk about your research ideas, if you'd like. The research topics were due today doesn't have to be by 5, just anytime today. You write me a little blurb. I'm thinking about this. The more specific, the better, so I can get a better idea. Some of you have sent me really broad topics, which is fine. So I hope you stay after today so we can kind of specify. And you never know. If these are really good, I'll put them up on Archive or something. I mean, especially your final paper. So Archive is this database of publications. But the problem is it's very hard to get an Archive if you have no academic affiliation, or you always need an endorsement from someone to get on there. So it's a very closed kind of thing. But I have my own academic license and I've gotten an endorsement. So if they're good, I'll endorse it and we'll put it up there. Probably under the physics education. There's a physics education section. So these would be good to share around with undergrads and students if they're good. So that's something to think about too. So we can just, I think today's lecture is going to be pretty short. I don't think we're going to need more than 45 minutes to an hour, because there's 2 ways to solve the harmonic oscillator. There's the algebraic method, which is using these creation and annihilation operators. And then there's the power series method. The power series method is really, really complicated. And you need a lot of complex math. So I'll show you the result from the power series method, and I have the calculation. I can do it, but I don't think it's going to be very insightful, especially when you see how brilliant the algebraic method is. But I do encourage you, if you want to continue down this path, you should look up power series method solution, and you should try and work it out for yourself, just because there's a lot of good mathematics in there that we'll be using a lot in field theory especially. So I would look into that, but it's challenging. It would take me a few hours to really explain all the nitty-gritty details of that. So I don't want to belabor us. Okay, so let's talk about harmonic oscillators today. Why don't we? Also, I have a request now. I'll say it one more time. I feel like the class is sort of shortened to our official size. So, I'd really like it if you could have your cameras on. If you can't, it's okay. But I'd really like it if you could, because we have, 10 people, and half of them I'm looking at black screens. So it's kind of, so again, it's fine if you can't, but that's just my request. Okay, so let's begin. So we all know what a harmonic oscillator is, right? Should we do a very basic review? Okay, let's do a very basic review of a classical harmonic oscillator. So basically a harmonic oscillator, a harmonic oscillator type system, classically is like you have a wall, okay, and you have some mass, M, and you have a spring attached to it, right? And this is your harmonic oscillator. And I talked about this last lecture, but now I can pull this box out, let it go, and the spring is going to jiggle and oscillate. Okay, I can pull it out even more. I can change the mass. I can change the weight of the string. I can do all sorts of crazy things. And trust me, you'll spend like a month on this in classical mechanics, doing all kinds of weird things. You'll add damping and all kinds of things to this. Okay, and you know, it has general solutions of sines and cosines. Now, why is it such a great system? Why are physicists obsessed with it? Because a lot of things in nature can be modeled by oscillations. Many, many, many things can be modeled by oscillations. And so it's a very interesting system. In fact, and I'm going to give you a very, very hand-wavy conceptual explanation of why quantum field theory is just a bunch of harmonic oscillators, okay? I'm going to do it now. Usually in a quantum mechanics class, most of the students will not take any quantum field theory. So there's no need to explain sort of where we would go with this stuff, but I'll do it. So, you know, in quantum mechanics, we've been talking about particles. Particles being the most fundamental object that we're working with, right? We're working with we will be working with electrons and protons and actual particles pretty soon, next lecture, with the hydrogen atom. However, in field theory, you go one step below. You start with fields. You all know what fields are, right? Just from physics, right? So a gravitational field, right, is just some area of space that has points labeled at each point. And at each point, you have a value for gravity, or how strong the gravitational field is. So similarly, in quantum field theory, you're dealing with a quantum field. And the way to think about it is that all particles and all forces come as excitations of that quantum field. Okay. What does that have to do with oscillators? Well, there's a great analogy by this guy, Anthony Z, who's a very great physicist, who wrote this great textbook, Quantum Field Theory in a Nutshell. And as you'll see, I'll recommend to you about 20 quantum field theory textbooks when we get there, because there's so many textbooks on the subject. And he writes that quantum field theory is just a large mattress with a ton of interconnecting springs that are oscillating at each excitation. So that's his whole conceptual picture, that you have this huge mattress, okay? And any excitation, and an excitation comes as a result of a force or an interaction, is just corresponding to some oscillating spring on that mattress. So it kind of takes all this abstract mathematics and condenses it into a nice conceptual picture. So these are very important systems. Okay, and you know, classically we work with some basic equations. So let's get into that now. So we have our famous F equals minus kx, which I hope you've all seen, right? This is just, k is the spring constant, depending on what spring you have and that sort of thing. And x is the distance you pull that thing out. And we have that m d2x t squared equals minus kx, right? This is just from classical mechanics, right? And then we derived last time that we have this nice expression as a differential equation for this same exact system, just packaged in a different form, where omega is the natural, omega naught is the natural frequency, k over m root. Okay. So this is just sort of the classical equations, nothing fancy, very, very straightforward. And this has solutions of a cosine omega t plus e sine omega t, right? So we can write these. Also, you should just keep this in mind. We can also write these as exponential solutions, right? Same idea. Sometimes it will be more convenient to write them or one way or the other. Okay, and in classical physics, you're always dealing with a potential v of x equals 1/2 kx squared. Okay, so hopefully that's all just familiar stuff from your physics class. Okay, so now we want a quantum mechanical analog, right? We want a quantum mechanical potential. We want a Hamiltonian, right? And then we want to solve the Schrodinger equation. By the way, I'm going to stop saying time-independent Schrodinger equation just because it gets annoying. When I say Schrodinger equation, I mean time-independent. Actually, it turns out there's very few situations where you actually need time dependence. Okay, it's not a very, which is kind of interesting. Could be another interesting topic to write about, but there's very few areas where you need time dependence. So I'm just going to say Schrodinger equation. I mean time independent. Okay, great. So let's just look at some random potential and let's observe something. So if I have some random potential, right, call this v of x, call this x, right, and it's doing all sorts of weird things, right? It's just moving around in space and time. There's a theorem, and you might have heard of this in your mathematics class, that any potential is approximately parabolic at the minimum. Okay, so at the minimum point, I can approximate any potential to be parabolic, right? Okay, and therefore I can write a pretty. By the way, that's why am I showing you this? I want to show you how you actually get this form of a potential. This is not the whole story. This is some approximation that we made because of this fact. So what do I mean by this? It means that I can expand v of x, okay? I can expand any arbitrary potential as a Taylor series about this minimum, okay? And don't worry if you miss this step. Really, I'm just showing you how people get this, just so you sort of know. Because every potential you can do this with, and you might have some really complicated v of x, and you might want to simplify it into some tight expression. Then you can Taylor series expand it about the minimum point. We'll call it x naught. Okay? So let's just write out that Taylor series. So I have v of x equals v of x naught minus v of x naught prime, x minus x naught, plus v of x naught double prime, this prime should be here, times x minus x naught squared minus dot dot dot. Okay, that's just the Taylor series expansion. This should be a double prime, and I think actually, wait, let me think about the signs for a second. Yeah, these should all be pluses, and this should be a 1/2. If I missed that 1/2, this was a stupid exercise because it's like, where'd you get the potential? And of course, you have higher order corrections. Okay, so I'm just showing you this because you might need to do it at some point in your life, and you want to know what to do. Okay, and basically, I can get rid of higher order terms. I can get rid of this. I know that this v double prime is going to be a constant, right? As a result of this, because it's just these primes are derivatives, by the way. I know I hope we don't get confused between dots and primes. I don't use primes really at all because dots signify time derivatives. Again, so basically I can rewrite this potential and approximate it as just my second term. About the minimum, and I mean here it's a general potential, but really v double prime of x naught is treated as some spring constant k. Okay, so you can see how we get this sort of, and you see this is x, this is basically a distance, right, between 2 points, and so you can just see how we get any potential. That's why I'm showing you this, and it's a good mathematical trick to know, right? It's a good approximation scheme. Mathematicians cringe at any approximation the physicist makes, but that's okay. We're not mathematicians here. Okay, so now we have some potential. Well, then what's the quantum mechanical potential? That's the key. So our quantum mechanical potential is v of x equals 1/2 m omega squared x squared, where omega is a frequency. Actually, wait, is it m or m squared? Wait a second, let me think about this. It's m squared. I'm 99% sure. Sometimes I forget. Let's just keep an eye on this as we do some calculations. That's the best part about physics, folks. You don't have to remember anything, because if you get things wrong, you'll find out sooner or later. Maybe after some algebra, but you'll find out if you missed a minus sign or something. Okay, is all this clear? This should be very like cursory, nothing really very confusing here. It's just, I'm sure you've seen things like this in your calc class. Maybe you haven't, maybe you have, I'm not sure. Maybe in your own self-study, you've seen Taylor series approximations, they come up everywhere. Okay. Which, by the way, if I were you, I would go on Wikipedia and I do this thing, this is a good tip. I don't know if it's a good tip for you, but I have this little notebook it's a very small notebook, and in it I keep all the equations that I think I'm gonna need to use, okay? So any expansions or so on. So it's a little journal. And I have the Taylor series expansions for sines and cosines and that kind of thing. Just use them all the time, and even in your research, sometimes it's better to approximate. You get more physics out of it. So that's very, very good. Okay, any questions? I'm going a little slow because we don't have too much to do, but I'm going to speed it up a little bit now. Okay. Excellent. Okay, great. So what's the idea now? Well, we have an equation of motion, the Schrodinger equation, and now we have a Hamiltonian, right? We have a potential. Now we solve. So let's just write out our Schrodinger equation. Again, total derivatives, time independent. I have no time dependence here. Hamiltonian is the total energy of the system. That's equal to the total energy. Okay, so now our whole goal for the harmonic oscillator is just to solve this thing. Seems straightforward, right? Not very different than the infinite square well, except for this very non-trivial potential. Infinite square well is more trivial. Okay, so now what's the key to solve this? What should we do? So the two methods again are the power series expansion, which is very long and brutal, and the algebraic expansion, where we're going to introduce these operators, which are so important. You need to know them really well. In fact, I would practice with them after this class or next week, because there's no problem set, because they're very, very important, the conceptual basis of them. Okay, so the first thing I'm going to do is I'm going to write this in a very, scandalous form, okay? Just to sort of work with this a little better. Okay, I'm going to write this in this form, which is equivalent. Okay, so I've sort of reformatted my equation. And you might say, why did he do that? Well, because it's going to be much easier to solve it in this form. Usually when you have some complicated thing you want to solve, the first thing you should ask yourself is, what can I do to it algebraically to make it more approachable? That's always what you want to do. Okay. So the idea is I want to factor this piece, right? My goal is to factor this piece with the hopes of solving this object, okay? So if I had two numbers, u squared plus b squared, just two complex numbers, and I wanted to factor this, this would be very, very easy, right? This would just be u plus ib times u minus ib, right? And that would give me that. However, we already know that we're going to have a lot of difficulty here. Why? Because we're not dealing with numbers in quantum mechanics. We're always dealing with operators. And so we need to be really careful about what we mean here. As I'm sure you've seen in the homeworks, the order of operators matter, right? If I have well, not with unitary operators, but with most operators, the order does matter, right? And so just keep that in mind. But the idea is we want to factor this piece. and see if we can do something with this. That's why I wrote this in this form. And we're gonna kind of just ignore these two for now. Again, see what we can do. So now I want to introduce an operator. Okay, we'll call it A hat plus minus, okay, plus or minus. And this is just equal to 1 over the square root of 2m, okay, of h bar over I d dx plus I m omega x. Okay, so now I've introduced an operator. This should be a plus or minus. And these are going to be our raising and lowering operators, okay? Or creation and annihilation operators. Also, I've written the hat here. I will never write the hat again because there's going to be way too many A's popping up now. So I did it only for you guys, just to hammer home it's an operator by popular demand. But I'm not going to do it ever again now because there's just too many A's. Okay. So, okay, now I've constructed, you know, and these things are arbitrary constructions. This is something you have to understand. This is just a mathematical construction. And the hope is it's going to help me solve this. And the fact that it gives me some new physics is even better, okay? Okay. So let's just do some exercises with this. And let's see how it works. And let's see, first of all, the goal should be, I have a raising operator and a lowering operator. So what should our intuition already tell us? We have some ladder of energies, energy eigenstates, right? And we want to go up and down the ladder, right? It's a discrete ladder, so there's no in-between chunks. We're hopping from one rung to the next, and the goal should be that this operator takes us up and down the ladder, okay? So the intuition should be very, very clear, but I want to make sure it works, because with angular momentum, it was very abstract, and we didn't make sure it worked, and I just, oh yeah, these things will take you up and down. And you know, if you wanted to spend 4 or 5 hours, you would have figured it out. But here I'm going to do the computations, okay? And we're going to get the energy eigenstates. We're actually going to work it out, just so you can do it. I know you can do it. Okay, so what kind of exercise do I want to do? Let's do the following. Okay, first of all, let me just rewrite some stuff. And again, we're going to have to be careful with multiplying things because they're operators, but it won't be too much of a problem. So let me just write out again my factorized Schrodinger. So the intuition hopefully is clear. If anyone has questions, you can let me know now as I rewrite, so I have more room. Also, a quick tip. It may seem that i's are disappearing all over the place, right? That's because of the properties of I, right? I squared is -1, plus I times minus I is 1. You should just know those so you're not like scratching your head. What did the I do there? Okay. Okay. So let's do the first exercise. Let's see what we get if we do A minus times A plus on some test function, f of x. Just some arbitrary test function. Now, the thing to remember here is whenever you're trying to explore operators, you should always have them act on some random function and see what they do. That's a good way to see how they behave. Okay, so now we're going to work this out. This one, okay. Okay, so let's just work this out. We have 1 over 2m. I'll get rid of the square root. Right, and then we have h bar over I d dx minus I m omega x, right, times h bar over I d dx plus I m omega x on f of x, right? So I have my lowering operator, I have my raising operator. Okay, now it's just a matter of working this whole thing out. So let's just do it. Let's just crank away. So first thing I'm going to do is I'm going to act this on this function. So then the first term just stays the same. And feel free to work this out on your own as I do. See if you get the same answer. Okay, you can work at your own pace. This becomes a df dx plus I m, yeah, omega x df x. Okay, and now I'm just gonna do this multiplication out, okay, which is not so complicated. Wait, did I do something wrong here? Yeah, I already did. Where'd this derivative even come from? This should just be an f. I'm jumping ahead. I'm like, well, where did that would be pretty bad if I had that extra derivative, right? So I have the 1 over 2m, right? And I have minus h bar squared. This is just d2f dx squared, right? Plus, right, the i's cancel. So then I have h bar omega x f. Sorry, and then this derivative is acting. This derivative is acting on x, d dx, and f, remember, because f is a function of x, right? So this is going to have x dependence. And then when I do this term, what do I get? Someone want to yell out? It's just minus h bar m omega x df dx, right? This derivative does nothing to this because it's just acting on f explicitly, right? And does someone want to give me the last term? What does this give? Just give a plus m omega x squared f, right? Okay. Okay, so now I've multiplied this thing out. Move this eraser off the board. Any questions on the algebra? It's all okay? Okay. I don't want algebra to stop us. I'm going to do something a little, how should I put this? I'm going to do something kind of interesting. So what I'm going to do is I'm just going to rewrite this in a form that we can do some more damage with. Let me just make sure I'm going to work this out right. Yep, so I can rewrite this as h bar over I d dx squared plus m omega x squared plus h bar m omega f of x. Okay, and to get this, let me just make sure I give you the right form that I used. I use this property. So to get this, I use this property. So if I have dxf dx, right, I can rewrite that expression as x df dx plus f. Okay? So you can work out how I got from there to there. It's just algebra. I skipped some steps. I'll erase up here, and we'll move to the top. Okay, any questions before I continue? We're okay, right? Okay, good. Okay, and now I'm starting to get a little excited. I'm like, wait a second. This kind of looks like my creation annihilation operator from before that I was kind of working out, except with this little bit of junk, right? So let's drop f of x. Let's get rid of the test function, which we can do. I mean, that's just a test function. So drop f of x, right? And what am I left with? I'm just left with 1 over 2m h bar over I d dx squared plus m omega x squared plus h bar m omega That's it. Can I erase these two expressions? Is that okay? Okay. See, this I like. Now I get head shakes. Now I know what to do. You know, if I'm looking at 5 black screens, I have to guess, and I don't want to do that if you guys are. Okay, so let me do something really stupid, but that actually helps me a lot. So if I multiply this 1/2m by everything, it kind of makes no sense, but I know that this form gives me some creation annihilation operator combination. So what I'm going to do is I'm only going to multiply 1/2m by this term, okay? So I get my final expression, 1/2m. And again, I'm going to just make sure that this stays the same. Okay. And I multiply the 1/2m by this, and I get 1/2 h bar omega. Okay, so that's my final result. Okay, now here's a very interesting thing. This, by the way, remember, this is my, this is the a minus a plus, right? Acting on f of x. Okay, and it's given me a very nice sort of little thing. And I can actually now, using this, I can rewrite my Schrodinger equation as creation annihilation operators, as combinations. So now I can rewrite my Schrodinger equation in the following way. A minus, a plus. Now, here's the sign issue. Is it minus or plus 1/2? It's minus 1/2 h bar omega on psi equals e psi. Okay. Now, of course, please remember that the order does matter. So this was a minus a plus. So what's a plus a minus? I'll just write out the expression. I just remember it because it's just a sign difference. Oh, let me just make sure. Yeah, it's just a sign difference here. Omega x squared minus 1/2 h bar omega. So basically our whole factorization procedure didn't really work out because we have this extra junk, right? This term like popped out and you can't get rid of it. You're going to have, I mean, if you did it a little differently, you might have a different prefactor or whatever, but this junk is there. Okay, pretty cool. Nothing really physical here. It's just like, okay, you've written this in some nice form. Okay, but that's what we have to do sometimes. We have to play around with things and see if we can get them in a more workable form. Okay. Everyone is okay. We're all clear. Okay. And please, please feel free if something's confusing to say. I think we have a big epidemic in America, I'll say. People are very afraid to get things wrong. But the reality is, if you want to do this as a career, any academic career in general, not just physics, any academic, you're going to be wrong a lot. So you might as well get used to it now. It's not the end of the world. That's why I'm going a little slower, because I want to make sure you really get this stuff. This stuff is super important to understand. Okay, but we just did algebra, so, okay, fine. Okay, I'm going to rewrite my new Schrodinger equation up top, and then we are going to work out something else. So for the harmonic oscillator, I have a new Hamiltonian. Okay, and now I'm going to make a the crucial claim of the class. Okay, now we're going to get to work. Now we're going to get to business. Again, similarly, I'm just going to do this just so I know that there's no confusion. If I have the opposite, this sign just changes. And I encourage you to work out the algebra. Okay, so now I have my Schrodinger equation. Now I make the claim of the class, the claim that you should be asking yourself, that you should be saying, I wish to test this claim. So what is it? This is the claim. psi is an energy eigenstate with energy, so the eigenvalue, energy E, okay, then A plus on psi, okay, is, and I'm just going to write PE for energy eigenstate, with eigenvalue, with energy E plus h bar omega. Okay, so I'm saying that it's going to take me up one energy level, exactly by this multiple, h bar omega. And that's what I want it to do. So we'll write this in bracket notation. So if I have E hat on psi equals E psi, right? This is our eigenvalue equation. If I have A plus on psi, I get E plus h bar omega on psi. Okay, that's what I'm saying. Now, before we, I'll give that aside at the end, sort of how this manifests in field theory. Okay, so this is really the crux. This is a big claim because this is basically telling you that these creation, I have to stop saying creation annihilation. It doesn't make sense in this context, but that these raising and lowering operators actually raise and lower states, which would be awesome. That's what we want them to do. But it's not obvious. Okay, I don't think it's obvious that, I mean, you can try to prove it. That would be fun. Well, I mean, we're going to prove it now. But if you guys can kind of see where I'm going to get that, feel free to shout out. But I don't think it's entirely obvious just by glancing. Okay, so what are we going to do to show that? And then similarly, you can do the other analog, that A minus gives you the state E minus h bar omega. Okay, it's just going to take you down. So now let's just work that out. Let's prove that. Okay, can I erase this statement? I see people writing. I'll give you guys a second. By the way, when I say proof, you guys have done basic proofs in geometry and things, right? So so basically, when a mathematician says proof, that's what they mean, what you did in geometry. When a physicist says proof, it just basically means we're just going to show that this actually works, just with some algebra and plug it in. That's it. That's a big difference. So we're not doing any rigorous proofs here. That's why I did not become a math major. Okay. Okay, let's do it. Let's work it out. This is really, I mean, this is the whole point of these things. If they don't do that, we're going to have to start from scratch. So let's just explicitly plug it in. So I have my Schrodinger. We'll use this version, right? And instead of psi, I have a plus on psi. Okay? So let's work this out. Now we have to be kind of careful because we have operators. But you know, it's nothing crazy because h bar and omega don't care about a plus. Okay? Okay, so I have a minus a plus minus 1/2 h bar omega a dagger. Oh no, not dagger. Plus. Sorry, I'm so used to daggers. You'll see why. Oh my God. Okay, that's the trivial manipulation. Just multiplied it in. Now I'm going to pull it back out. You'll see why. And now I'm going to do the most trivial move you've ever seen in your life. But when I show you this move, folks, it's life-changing. Okay? This is a life-changing trivial move. If I have the number 1, oh, no, sorry, wait, I don't want to do this. Wait, let me think about this. I can't ruin my trivial move. Right, okay, if I have 1/2, okay, then that equals 1 minus 1/2. Okay, this will change your world. This will change your world, believe me, because I'm going to do that right here. I'm going to do that right here, and you're going to be like, why? But you'll see. So I'm going to use this very, very deep mathematical formalism to extract this. So this becomes a, let me just make sure I do this right. Yeah. This becomes a minus 1/2 h bar omega plus h bar omega on psi. Yeah. Very, very deep. And now we should start to see something pretty awesome. Okay? I told you, this is going to change the world. Right. I have my Hamiltonian here. What's my Hamiltonian? It's an energy. Okay? And then I have this plus h bar omega, which is what I wanted. Okay, so I'm getting there now. And then I have an A plus, which is also what I wanted. And then I have a psi. So everything's gonna be just fine now, because now I have A plus, I have an energy plus h bar omega on psi, which I can rejigger this because the A plus is acting on psi. It's not acting on energy. It's not acting on the Hamiltonian. It's not acting on h bar omega. And I get exactly what I said I'd get. There you go. So we have proved that our raising operator works in this fashion. Okay, albeit we use some very, very fancy mathematics at the end, but we got there. So this is great. Any questions? And you know, I should just write this, QED, just to spite the mathematician. We do real proofs. By the way, we have a physics podcast called QED. You guys are ever interested. Okay. Okay, and I mean, you could do the same game with A minus. I'm not going to do it. But, you know, I'll just write it here that with A minus, you're just going to get E minus h bar omega, A minus hat on psi. Pretty cool. Pretty cool.
This might be a dumb question, but
Such thing.
in your second to last equation, why is it negative 1/2 h omega plus h bar omega instead of,
well, think of it this way. If you have this would be a minus 1/2, this would be a plus 1, right? And then this would just give you this thing back out.
But then the equation right before it is also minus 1/2 h bar omega.
Yeah, that's fine. I don't see the sign issue there.
Okay.
I don't work it out. I mean, there's no sign issue. That's legal.
Okay.
I mean, technically, I could have changed the signs, but that would kind of screw us up here because we want a certain result. But they're equivalent. Okay, now basically what you can think about is we can form some ladder of states, right? Now we can form some ladder of eigenstates. So let's just do that. Wow, I said it was going to be a short lecture and it's already 10:20. That's crazy. I really thought this was going to go. That's what happens. You always think it's not a lot of material, but it is. Okay. So let us write out the ladder of states. The first thing I'll say is you need to have a lowest level of the ladder, the lowest rung, right? Because you can't have negative energies, right? So the first thing I'll postulate is say that A minus on the ground state, we'll call that psi naught, is just 0. And that's my lowest rung of the ladder, okay? That's kind of trivial, but it's important. And now I can rewrite my raising and lowering operator as the ground state, okay? So now I can just do this. Psi naught x minus I m omega. Yeah, I m omega x psi naught equals 0. Okay, this is just my lowest state, right? This is this quantity here. A minus acting on psi 0. Makes sense? I just wrote it out explicitly. And doing some algebra, I get this thing. D psi 0 dx equals minus m omega h bar x psi naught. Let me just make sure that's right. Yeah, it looks good to me. So if you move, just work out the algebra. Shouldn't take too long. And you get something like this. Okay. Now, this is a differential equation. Okay. We saw some differential equations last time. And I told you one way to solve them was this technique called separation of variables, right? So now I'm going to show you how to do that here. So the most basic way to solve a differential equation, which you learn, is called separate the variables and integrate both sides, okay? So I can separate it. I have a psi naught, I have a d psi naught, right? And then I have a dx and an x. Now mathematicians would absolutely cringe at this. Okay, they will never solve a differential equation like this because we just treat this as a fraction, okay? Mathematicians would say, no, 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 but it's okay. It's a very useful technique. So let's just do that. You're kind of learning way ahead here, even though it's very simple stuff. So what do I get? I just get a 1 over psi naught, d psi naught equals minus m omega over h bar x dx, right? And now we, as promised, we integrate both sides. So I integrate the right side to solve this equation. Pull my constants out. Okay, this is super easy. This will give you what? An ln, right? This will give you what? X squared over 2. What do I get? I just get ln psi naught equals minus m omega over 2h bar x squared, right? Okay, and now I have a solution. I have a general solution, right? I can just solve this thing using my properties of logarithms. And I get that psi naught, my ground state, is just an exponential, right? Some constant, a naught. This should have some constant, right? I mean, I just absorb it. It's not really a big deal. E to the minus m omega over 2h bar x squared. Okay? So we've solved this equation using a very, very, very basic technique. So even if you didn't know how to solve this by looking at it, now I hope you just know that these are very trivial. I mean, this is like a 1 second thing to solve. They look daunting, but they're not, right? And you solved it. And it makes perfect sense. It's some exponential by some multiple of h bar. I mean, all of the same things are going to keep popping up, right? So your intuition should be starting to develop here, because we're starting to see the same kinds of expressions pop up. Any questions on what I did here? Everyone knows how to do these integrals, right? It's not new to people. If it is, it's totally okay. Just means that you have to come and I have to teach you integrals, which is totally fine with me. I hate integrals, but I will. Well, these are okay, but like when you actually, you find out that you can't do most of them by hand. Most of them you have to do in a computer. Okay, excellent. Okay, so we've worked out some properties of the ground state. And if you plug this into Schrodinger, you get that psi naught is just equal to, well, it wouldn't be psi naught, it would be E naught. You get that your ground state energy is just 1/2 h bar omega. Okay, so if you plug that into Schrodinger, you can do that as an exercise into our creation, keep saying that, into the raising and lowering operator Schrodinger equation, plug in this as your psi naught, right? And you will get this as your energy, okay? So this truly is a ground state. That's the point I'm trying to make. This truly functions as a ground state based on this condition. Now, if I postulated that A plus psi equals 0, I mean, you could work it out that way too. You just get something a little different. Okay, so now I'll erase. That's kind of all there is to it. Now I can write out the ladder of states. Okay, so let's draw out the ladder of states. So I have some ladder. I have some ground state E. And at E, ground state E, I just have the state psi, right? And I can start going down the ladder. I have E minus h bar omega, right? And this would be what? This would just be A minus on psi, right? Then I go down another run, A minus 2h bar omega. This would be A minus squared on psi, and so on and so forth. Okay, we'll do one more. Just to show you, make this a huge ladder. You know, and then I could go E minus 3h bar omega, A hat minus cubed on psi, and so on and so forth, obviously not going into negative energies. Okay, so you know, this is just applying A minuses. This is going up in the energy and applying A pluses. So what do I get here? Well, I get E plus h bar omega, and then I get E plus 2h bar omega. You know, you can play around with this. You should try and compute A squared on psi. Okay, makes sense? Now we have our ladder of states. Okay, now for the power series method, I'm going to skip all of this craziness and I'm going to show you the solution you get. I just wrote it down here. Where did I write it down? First of all, you're going to need the fact that rho is just something that goes m omega over h bar. Yeah, x, that's what we called it. For the power series method, and you get solutions that look like this. Oh, by the way, before we do that, that's fine. I mean, it doesn't matter. I mean, now you can apply to n states, right? Okay. Okay, fine. you get a solution that looks like this. I have it down somewhere here. Yeah, so it looks, the reason I'm going to show you this is because what you use to solve it is very, you're going to see it. They're very famous. You get n omega over nh bar to the 1/4 over 1 over 2 to the n factorial hn rho e to the minus rho squared over 2. Wow, you get all these weird things, which is fine. That's just because of the method. But what's important is to look at the structure. You have the same exponential structure. It's going up by multiples of n. And I have them parameterized by some weird function that's moving them up and down. So now instead of the raising and lowering operator, in the power series method, these things are moving them up and down, these h of n's. And these are the Hermite polynomials, which are really famous. So let's just write down some Hermite polynomials, which are important. That's the only reason I'm even bringing up the power series method. So h naught equals 1, and there's some formula for computing them. They're on Wikipedia, but you know, probability theorists use a different convention, and so on and so forth, and you can compute these forever. They're orthogonal polynomials and dot, 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 whatever. I mean, they're just numbers. Okay. And I have one more thing to show you, and then we're done for today. So it did end up a little early. If we did the power series method, we'd be here till 12. So I was working it out myself, and I said, oh, this is so painful. I don't want to, because you know, I haven't done it in a while too. So I said, can I do it again? Can I figure it out? And it was painful. Okay. Okay, so we solved the harmonic oscillator. We've done it. So pat yourself on the back. That's one big system done. Now we just have the hydrogen atom. That one is going to be more tricky. It's not just algebraic. We're going to need to really introduce special functions. Okay. So let me draw you some states. So I went on Mathematica. I used our expression for psi n, and I just plotted some states of the harmonic oscillator. So let's see what patterns we can observe, and then we're done. See, to me, that's the biggest difference between classical mechanics and quantum mechanics. Classical mechanics, when I give you something to solve, it's very intuitive. Oh, it's a velocity. Oh, it's a ball at this, but this is not very intuitive. This is a bit more abstract, okay, with what you're actually getting out from a computation. Okay, so I plotted some psi's. So this is how they look. So psi, the ground state, is literally just a centered Gaussian. The first excited state is an odd function, so it's not going to contribute. So this kind of looks like our infinite square well. But actually what ends up happening is as you go up the ladder, second excited state, they get more and more eccentric. Okay, and then the third excited state, and I'll show you something cool. Okay, you know, they get even more wild and oscillatory. Okay, so we're getting crazy. And the 100th excited state, okay, I just plotted it just to show you how crazy they get. My drawing was going to be terrible, but you get the idea. Is like some crazy oscillation with 2 peaks. So which makes sense. I mean, the more and more energy you're going to pump in, the more dramatic the oscillation is going to get. I mean, that's just common sense, I guess. Okay, and obviously we did this in 1 dimension. There's a 3-dimensional oscillator. It's trivial, the extension. Okay. Now I'm going to show you how this comes up in field theory, very briefly, for a few minutes. And then we'll take a little break and we'll come back and talk about your papers. And I'll stay at the board. This way, if you want to work something out on the board, we can write it down or do a computation or whatever. Okay, so let us talk about field theory very briefly. Okay, so let's write our rate. And you've noticed I've been very confused with my terms because I'm used to the field theory analogs. So if you have your raising and lowering operator, you just discovered that you're moving up and down the ladder of energy eigenstates. Okay, that's what we've derived. Isn't this great when you can write down such a short expression and you know exactly how it works now? And you know how much machinery is behind it. That's what I love. You know, when people write out this short little expression in like general relativity, in my head I'm going, oh, that's such a long thing. So, which we're going to need to know tensors if you end up doing research with me. That's a must. Tensors are super important. But the analog to A minus and A plus in field theory, so this is QM, and then in QFT, we use A dagger and A. Okay, and these are creation and annihilation operators. So what do they do in field theory? Now, they don't take you up and down energy eigenstates. Now they create and destroy particles, literally. So if I had the vacuum, that's no particles, the vacuum. Some people will also label this as omega. That's why I called it dagger earlier. I was lost. If I apply A onto the vacuum, I get nothing back. I get zero because this is going to destroy anything that's in there, and there's nothing in there. If I do A dagger on the vacuum, I get some particle out. We'll just call it AN. I get something out. Okay, so they literally create and annihilate states. Okay. Another very, actually, I don't want to get too much into this, but that's the conceptual reason why these are important, and along with the fact that they take a very similar form. Okay, but I'm not going to get into the details. That's why we have next term. Okay, wonderful. Okay, so that's the harmonic oscillator. I really hope that the class is becoming more comprehensible now and less abstract. And the goal should be that you can do these kinds of things on your own and use these kinds of tricks and find your own tricks. That's the point, okay? Okay, great. So it is 10:35. I think we should take 5 minutes because it's early. And I will come back and we can discuss anything. We don't have to just discuss your papers. We can discuss anything. I put aside this next hour for you guys. So I'll be back in 5 minutes. I'm just going to get a quick snack, okay? Okay, great. How do we want to do this though? I think I'm going to leave my phone going, this camera going. And yeah, we can discuss like this. So if you need the board, we can use the board. Okay, so I'll be right back. Let me stop the recording.